Today we're going to learn about isotopes. So if you remember in the last lesson, I said that you can change the number of neutrons, you can change the number of electrons, but you can never change the number of protons because your protons are your identifier, your social security number for the atom. Well, today we're going to make one of those changes. We are going to change the number of neutrons. Okay, so we're going to talk about isotopes. So what are isotopes? Isotopes are atoms that have the same number of protons, but a different number of neutrons. So what does it mean to have the same number of protons, but a different number of neutrons? So if you remember from the last lesson, I said all of your weight is in your nucleus, and that is being determined by the number of protons you have and the number of neutrons. We can't change our protons because it changes the identity of the atom, but we can change the number of neutrons. So if you change the number of neutrons, you're changing the weight of your atom. So you can kind of think of it as you as a person. If you gain a few pounds, you're a little heavier, but it's still you. Or if you lose a few pounds, you're a little lighter, but it's still you. That's all we're doing. Your atom is gaining weight or losing weight, but it's still the same atom. Because its number of protons are the same, its number of electrons are also still the same. They haven't changed. The only thing that has changed is the number of neutrons. Neutrons are not involved in chemistry. The only things really involved in chemistry are your electrons, and if you're doing nuclear chemistry, your protons. But because we're not changing those things, the isotopes behave chemically similar. And different isotopes of oxygen behave the same way. They're just a little heavier. Okay, so they're going to have different mass numbers because mass number is protons plus neutrons, but the same atomic number, same number of protons. Okay, all we're doing is changing the weight. Okay, it's got some COVID weight on them, or some COVID-19 quarantine weight on them, or I've lost some weight because I started moving now that we're moving around a little bit more. Okay. Let's talk about different isotopes. So let's talk about hydrogen. Hydrogen has 3 different isotopes, and they actually have names. These are used a lot in the medical community. Okay, let's start with hydrogen 1. Hydrogen 1, if you look at hydrogen on the periodic table, it has 1 proton. Its atomic number is 1. So hydrogen 1, which is one of the isotopes of hydrogen, we call it protium, has 1 proton. It has no neutrons, and it has 1 electron. Its mass number is 1. That's what this number means right here. Its mass number is 1 because it only has 1 proton. If you look at hydrogen 2, hydrogen 2, because it's hydrogen, still has only 1 proton. That's the little blue dot. But now it also has a neutron. So it gained 1 neutron. It gained a little weight. That guy's called deuterium. We didn't change the number of electrons. We didn't change the number of protons. All we changed was the number of neutrons. Now, because we have 1 neutron and 1 proton, its mass number is 2. Hydrogen 2. Okay. The third isotope of hydrogen we call tritium. And because it's hydrogen, it still only has 1 proton. It wouldn't be hydrogen if it didn't have 1 proton. But now instead of 0 neutrons or 1 neutron, you now have 2 neutrons. It gained a little bit more weight. So its mass number is 1 plus 1 plus 1, 3. That's hydrogen 3. We changed the number of neutrons, did not touch the number of protons, did not touch the number of electrons. Let's look at another one. Okay, let's look at the isotopes of potassium. The isotopes of potassium are potassium 39, potassium 40, and potassium 41. So because it's potassium, it has 19 protons. It has 19 protons in potassium 39. It has 19 protons in potassium 40, and it has 19 protons in potassium 41. It would not be potassium if it didn't have 19 protons. Okay? Again, isotopes are not changing electrons either, so your electrons are also 19 because we're talking about a neutral atom. We haven't talked about anything else yet. The only thing we're changing is the number of neutrons. So let's see how many neutrons are in potassium 39. So 39 is the mass number. So 39 minus 19 gives you have 20 neutrons. 20, your protons plus neutrons has to equal your mass number. 20 plus 19 gives you 39. On this one, for potassium 40, 21 neutrons plus 19 protons gives you a mass number of 40. For potassium 41, 22 neutrons, 19 protons gives you a mass of 41. So we talked about hydrogen having three isotopes. We talked about potassium having 3 isotopes. Not everything has 3 isotopes. There are some that have 2 isotopes. There are some that have 5 isotopes. There are some that have 4. There are some that have none. So it just depends on the situation, and I would have to tell you those. Okay, so there are 2 ways to write isotopes, and you've seen both of them. You just didn't know you've seen both of them. So let's start with the way I just talked about it a minute ago. We're going to talk about hyphen notation. Hyphen notation has 2 parts. It has the name of the element dash the mass number, or you can write the symbol of the element dash its mass number. So what does that look like? You can write carbon dash 14, where 14 is the mass number. The name of the element is carbon. 14 is the mass number of protons plus number of neutrons. Or you can write it with its symbol. The symbol for carbon is C dash its mass number. Chlorine has 2 isotopes. Well, right here, we're only showing one of them. Chlorine 35, its mass number is 35, or chlorine or Cl35. Or you can write it as hydrogen 3 for hydrogen, for tritium, hydrogen 3 or H3. Okay, the other way of writing this is the nuclear symbol. And you've seen this too. You saw this in the last unit. You just didn't know this was the way of writing isotopes. What you have is you have your element symbol written out. So if we're looking at carbon, you'd write carbon here. At the bottom left-hand corner, you would write the atomic number or the number of protons. 6. Carbon's atomic number is 6. Top left-hand corner, you would have 14. That is its mass number for this isotope. It's one of the more rare isotopes. Carbon 14. Sometimes, because chemists are lazy, they will omit the atomic number. They will not write the atomic number there because it's kind of redundant. Because if you have carbon, it's got to have atomic number of 6. Otherwise, it would not be carbon. Okay, let's try writing those 2 notations down. So here we have 2 atoms. We have 2 atoms. Let's write down both isotope symbols, both in the hyphen notation and the nuclear symbol notation. So first thing we have to do is we have to determine which element these are. So the way you determine that is by looking at the number of protons you have. In both of these atoms, you have 3 protons. So you go to your periodic table and you look, who has 3 protons? Well, 3 protons is lithium. We're going to write lithium. We're going to start with hyphen notation. Then we're going to write dash, and we need to write down our mass number. Our mass number is protons plus neutrons. So we're going to write lithium 6 for this one. 3 plus 3 is 6. And for the other one is lithium 7. Okay, that's hyphen notation. Now let's do nuclear notation. So we're going to write down the symbol first. The bottom left-hand corner, we're going to write the atomic number. Top left-hand corner, we're going to write the mass number. So we should have a 3 on the bottom and a 6 on the top for the first atom. And we should have a 7 on top and a 3 on the bottom for the second one. If you leave off the 3 at the bottom, that's okay because lithium tells you it's got an atomic number of 3, but you cannot leave off the mass number. Okay, so right now you should pause the video and take a couple minutes to see if you can fill in this table. Here you've been given the hyphen notation. With the hyphen notation, you should be able to fill in this entire box. You can use your periodic table to look up potassium, or you can just use the little box, the periodic table information that's given in this little box. So please pause your video right now and fill in this table. Okay, let's do some of these. So potassium because it's potassium, it has 19 protons. In this case, potassium, it's potassium 39. So 39 minus 19 gives you 20 neutrons. You have 19 electrons because it's a neutral atom, and the nuclear symbol should look like this. I'm going to display the rest of the answers, and you should check your answers from your box. Okay, now let's spend a couple, pause your video again and see if you can do this one. Again, it's the same idea, but here you have an atomic number, you have mass number, you have protons, neutrons, and electrons. There's also some questions on the top you need to answer. So pause your video and see if you can do this. This takes a little bit of practice just to kind of remember. It's not very hard, but to remember how to do it and remember the vocabulary and what it implies, you really need to practice. So please pause your video right now. Okay, so we've got the numbers here. I just want to point out a couple things. Again, as I said earlier in the previous video, part of chemistry is searching for things on the periodic table. Uranium-235 and uranium-238. These are used in nuclear reactors. This is very common in nuclear chemistry. But uranium is down in the very, very last row of the periodic table in the actinide series. For those of you that actually colored your periodic table like suggested, that is in the green column. Things down there tend to be radioactive and unstable. So uranium-238, which is the most abundant of the isotopes, is unstable and it does decay. You can check your answers from the table here. Okay, to review a couple things. First of all, this is the same slide I showed at the last lesson, but just to review, your electron has about 0 AMUs, your protons have 1 atomic mass units, and your neutron weighs about 1 atomic mass unit. But your neutron weighs slightly more than your proton. And the reason I'm bringing this up is right now we're about to do some math. If in a problem you are given the more precise values for your mass number, because it's taking into consideration these differences between the proton and the neutron mass, then you must use those more precise values. If it does not give you the more precise values and you're using the estimated 1 AMU, then you can use that. But if given the more precise values, you will have to use the more precise values. Okay, so we're going to talk about atomic mass. Atomic mass is what's found on your periodic table. It is a weighted average of all the isotopes of an element. Remember I said that you could estimate the mass number off of the periodic table? That's not completely true. What you can do is you can estimate the mass number of the most abundant isotope off the periodic table, because this is a weighted average mass of all the isotopes of an element. So where can this atomic mass be found? On the periodic table. It is the number with the decimal in it. It's a weighted average. When you're doing these math problems, you're going to get numbers with a decimal. Okay. As a general rule, when we're doing these problems, we've learned about significant figures here. I'm telling you to ignore that. And to round to the thousandths place. In other words, round to 3 decimal places. Okay? Generally. Okay, so let's talk about what a weighted average looks like. So let's do a non-science problem. So let's say you have you're in a class and they tell you that 80% of your grades are due to your tests, to your test scores, your test averages. And they say 10% of your grade is due to your homework grades, and 10% of your grade is due to attendance. And you want to calculate what your final grade will be. Well, let's see. Let's give some hypothetical grades. So let's pretend that your average for all your tests is a 72, not that great of an average. Okay, and the average for all your homework is a 50%, not that great. That explains your 72 in the test. You didn't do your homework or you didn't practice. And you have a 90% attendance. You have an average of 90%. So if you were trying to find out what your overall grade is in this class, recognizing that 80% of the grade comes from your test, 10% of the grade comes from your homework, 10% comes from your attendance, you can calculate a weighted average. But before you do that, you can have a rough idea of what your grade will be. For instance, if 80% of your grade is going to be due to tests, odds are that your final grade is going to be around 72 because most of the grade is coming from here. It's going to be closer to 72 than it will be to 50. It'll be closer to 72 than it will be to 90. So let's do a weighted average. The way you calculate that is you take your average that you got in the class times 80 over 100. That's just a percentage, 80 over 100. You can do this part right here in your head if you want. You can just say 72 times 0.8. Okay. Plus 50 times 10 over 100, or 50 times 0.1. Plus 90 times 10 over 100, or 90 times 0.1. You enter that all into your calculator. Your average is 71.6. Very close to that 72 that we said. We predicted that we would get a score of around 72, and that's where we are. When you're doing any problems in this class, please have an idea of where you're headed so that you can kind of have a self-check. You might not know the exact value, but you can get an idea of where you want to be. Okay? So generally, atoms of a given element will have one isotope that's in higher abundance, has a higher percentage than the other ones. The most abundant isotope is going to contribute more to the weight of your atom. Your weighted average that's on your periodic table, the atomic mass. So you can predict its mass number, the most abundant element. You can predict its mass number from the periodic table, but only for the most abundant element. Okay? So for instance, if you look at beryllium, its atomic mass is 9. So if you were to guess what is the most abundant isotope of beryllium, you'd probably say beryllium 9 because you're close to 9. Beryllium 9.012 rounds to 9. So probably the isotope that contributed the most to the weight, the average atomic mass of beryllium was probably beryllium 9. Okay. So if we were to look at argon, argon has 3 isotopes. It has isotope argon 38, it has argon 40, and it has argon 41. So looking at argon, it's got an average atomic mass of 39.948. So if you were to predict which of the isotopes contributed the most to this weight, well, this rounds to 40. Argon 40 is probably contributing the most to the weight. Okay. So how do you calculate average atomic mass? Same way we did the weighted average for grades, we're doing the same thing here. We're going to do the percent abundance over 100. You can do this part in your head if you want. Percent abundance over 100 times the mass number of that isotope plus percent abundance of isotope 2 times the mass number of that isotope. Plus, if you have another isotope, it'd be the percent abundance of that isotope plus its mass number of that one, and so on and so forth. Again, as I said earlier, protons and neutrons don't have exactly masses of 1 AMU, if you're given the exact numbers, then you must use those. Okay. So we're going to do a little calculation, but let's do some predicting first. So if you were to look at this, at chlorine, and you were to predict the most abundant isotope for chlorine, what would it be? So you got chlorine, and its atomic mass, the average atomic mass is 35.453. If you were to predict what is the most abundant isotope, you would probably predict that it is chlorine 35, because that rounds to 35, so probably chlorine 35 is the most abundant. Okay, there are two isotopes of chlorine. Okay, these are the two isotopes of chlorine. You have chlorine 35 and you have chlorine 37. Okay, and as we said on the last slide, we predicted that chlorine 35 was going to give you the most, was going to contribute the most to the weight. And yeah, if you look at the percent abundance, almost 76% of chlorine 35 contributes to that weight, and only 25% is due to chlorine 37. Okay, so you would expect the average to be around 35, and we know that. We did that in the last one, and you can check it on the periodic table. But let's do the math. Let's actually calculate the atomic mass of chlorine. So this is that same table from the other page. So we're going to calculate it. I'm going to show you two ways of doing this. I'm going to show you one way of doing it here, and then I'll do a different way for a different problem. Just different notation that you can use depending on how your brain works. So we're going to do, for chlorine 35, we're going to multiply the mass, atomic mass unit, is the mass number of chlorine 35 times its percent abundance. 35 times 75.770 over 100. You can do this one in your head if you want. Just move the decimal place over 2 places. And that's going to give you this number. Okay. For chlorine 37, you do the same thing. 37 times its percent abundance. That's going to give you a number. And now we're going to add the two. Okay. Now, if you look on your periodic table, it's very similar to what's in the periodic table, so we know we did it right. Okay, so that's one way to do it. Do one line at a time and then add them. Another way to do it would be something like this. Here you have copper. It's got two isotopes. They have mass numbers of 63 and 65. The relative abundance and atomic masses are 69.2% for a mass of 6293. So this one's this guy. But here we're getting a more precise number, so we must use this instead of 63. And we have 30.8 for 6493. We're going to calculate the atomic mass of copper. Okay, so we're going to start by looking at this one. We're going to do the percentage over 100 times its mass, 6293. That's copper 63, plus this percentage over 100 times 6493. You enter this into your calculator and you're going to get 63.546. You should all pause what you're doing right now and enter it into your calculator. There tends to be a lot of mistakes that are made with calculator entry. You can also check your answer on the periodic table. Let's try another problem, this time with an element that has 4 naturally occurring isotopes. Chromium has 4 isotopes. It's got chromium 50, chromium 52, chromium 53, and chromium 54. If you notice in this problem, our mass numbers are not very precise, so we can just use the 50, the 52, the 53, and the 54. This problem wants us to determine the average atomic mass for chromium. Okay, so we're going to start by calculating what is the contribution from chromium 50. Before we do this problem, we should look to see who has the highest abundance. The highest abundance is due to chromium 52. Look, it's got almost 84% of all the isotopes that are naturally occurring are due to chromium 52. So that's going to contribute the most to your weight. So you're going to expect your answer to be around 52. That kind of gives you a direction. So if you don't get something around 52, you know you did something wrong. So let's start with chromium 50. We're going to do the percentage over 100, or you can do that in your head, move that decimal 2 places, times 50. And that takes care of this one. Now let's do the next one. Chromium 52, 8379 divided by 100 times 52. Again, you can do the conversion of the percent abundance to an abundance in your head if you want. And then you're going to do chromium 53. And then you're going to do chromium 54. Please make sure you enter this into your calculator and practice. Make sure you use all those parentheses. And when you do that, you get 52.055 AMU. Double check it against the periodic table, too. For problems like this, when you can double check against the periodic table, you should. Okay, let's try another one. Carbon 12 makes up 98.89% of the naturally occurring carbon. Carbon 13 makes up the rest of the naturally occurring carbon. Use this information to determine the average atomic mass of carbon. Okay, so they're talking about 2 isotopes. Carbon actually has 3, but here we're simplifying it, saying there's 2. It says 98.89% of the carbon is due to carbon 12. The rest of it is carbon 13. So first of all, before you even do any problem, you know your answer should be around carbon 12. But to find how much carbon 13 there is, what percentage, you would subtract 100, this number from 100, okay? Which would give you 1.11% of carbon 13. And now we solve this problem like we do every other problem. Okay, here I converted the percent abundances in my head as opposed to dividing these numbers by 100 on paper. We get 12.011 AMU. And that's exactly what it says on the periodic table, so you did the problem right. If you can, you should always check your answers against the periodic table. However, you sometimes won't be that lucky. Sometimes you might be given a generic isotope. Isotope X, element X, doesn't exist. But in element X, we're saying that there are 3 isotopes, 16, 17, and 18. X16 has an percent abundance of 99.762. Isotope 17 has a percent abundance of 0.038. Isotope 18 has this percent abundance. It's asking you, calculate the average atomic mass and then identify which element it's talking about. So before you do this problem, let's look at it. This guy's contributing, isotope 16 is contributing 99.762% of the weight is due to this guy, to isotope 16. So that's probably your answer is probably going to be close to that 16. Just keep that in mind. Okay, so let's solve this problem. We're going to do this number over 100 times 16, this number over 100 times 17, this number over 100 times 18. You enter that into your calculator. You get 16.004. 16.004. Now you go to your periodic table. Which element has a mass of around 16? When you look, you will find that that is oxygen. This isotope, this problem we're solving is for oxygen. Okay. Neon has 2 isotopes, neon 20 and neon 22. Using information from the periodic table, predict which occurs in greater abundance. Who's contributing the most to the weight? Is it neon 20 or is it neon 22? Turn off your, pause the video, write down the answer on your paper, on your notes. Okay, because neon is at 20.180, that's closer to neon 20 than it is to neon 22. So neon 20 is contributing the most of the weight. Neon is a noble gas. That means it's all the way to the right side of the periodic table. It's in the very last column. Those guys are non-reactive. So when you see, like, you have neon lights The reason they're called neon lights is because they're filled with neon gas. Okay. Last problem. Calculate. I'm just going to give you the answer. If you cannot come up with the answer with doing the problem work yourself, just see me at office hours. Calculate the atomic mass of bromine. We're trying to find the atomic mass of bromine. And you should sort of know what it is just by looking at the numbers. It says the isotope of bromine has atomic masses and relative abundances of the following. So we're going to calculate it. So we've got this mass number, and that's 51%. This mass number, and that's 49%. So we have almost 79, and we have 81. Because they're about evenly split, you're going to kind of expect something in the middle between the two, except for maybe slightly closer to 79 than it is to 81. So when you do the math, you should come up with 79.906 AMU. Notice the units. Okay. Next, we will talk about electrons in the next lesson. Thank you.